In this video clip, we talked about polar equation and planetary motion. So we have a planet like the Earth moving around the Sun. So let's place the Sun at the pole. So this is the pole, or at the point 0, 0. And then we have the planet like the Earth moving around the Sun. And we know that the planetary orbit is in the form of an ellipse. It has an elliptical orbit. And therefore, let's call this point right here, let's call it the center of the ellipse. And then we have vertex number 1, we have vertex number 2. So when the planet is right here, that's when the planet is farthest from the Sun. And when the planet is right here, that's when it's closest to the Sun. And then when the planet's right here, then the angle theta is this angle right here. Then the distance from the planet to the Sun will be r. And then this point will be r theta. And what we want to do is find the polar equation for this ellipse. Since we have this type of ellipse, then we know that the directrix has to be over here. This is the center of the ellipse. Let's call the distance from the center to the vertex just like before. Let's call it A. And just like before, let's call the distance from the center to the focus, or the pole, or the location of the Sun in this case. Let's call it C. The distance from here to here is C, and then from the center to the vertex is A. And so when the planet is at this point right here, this is when R is the distance from the Sun to this point will be C plus A, or A plus C. And this is when the angle theta will be 0. Then of course when the planet is at this point, this is when theta is 90 degrees, or pi over 2. And then when the planet is here, theta will be pi, or 180 degrees. And then when the planet is here, theta will be 3 pi over 2, or 270 degrees. Now when the planet is at this point, that's when it's closest to the Sun. At this point, theta is pi. The distance from the center to this vertex is A. The distance from the center to the Sun is C. And so this part right here would be A minus C. So this point R would be A minus C, theta would be pi. From previous videos, we have shown the 4 types of equations based on the location and the type of directrix. For our example here, the directrix is to the left of the pole and is vertical. So we have a directrix that's vertical and to the left of the pole. So our equation will be this one, this polar equation. Directrix to the left of the pole, R equal to ED, 1 minus E cosine of theta. Recall that D is the distance from the pole to the directrix. So the distance from here to here, from the pole to the directrix, that's D. And then E is the eccentricity, which is C over A. So now let's go find the equation of this ellipse, of this elliptical orbit of the planet. So this is our equation, r equal to ED dividing by 1 minus E cosine theta. At this point, which is a point on the ellipse, r is A minus C, theta is pi. So we have r is A minus C, theta is pi. Cosine of pi is negative 1. So we have A minus C is equal to ED dividing by 1 plus E. Recall that eccentricity is defined as C over A. Multiply both sides by A, then we have C is equal to E times A. In the place of C, we have E times A. Common factor is A, so we can rewrite this as A times 1 minus E is equal to ED dividing by 1 plus E. Multiply both sides by 1 plus E. So multiply both sides by 1 plus E, then the right side we just have ED. 1 plus E and 1 plus E, that will cancel out. 1 minus E times 1 plus E is 1 minus E squared. So we have ED is equal to A times 1 minus E squared. A is the distance from the center to the vertex. And therefore the equation of this planetary motion, or this elliptical orbit, is r equal to ED 1 minus E cosine of theta. ED is A times 1 minus E squared, dividing by 1 minus E cosine theta. For the Earth and the year 2024, Earth is closest to the Sun on January 2nd this year at 6:38 p.m. And that's when the distance from the Earth to the Sun is 91,404 and 95 miles. So when Earth is closest to the Sun, so that's when the planet is right here, so that's when the distance from the Earth to the Sun is 91,404, 91,404,095 miles. And so A minus C would be this. Earth is farthest away from the sun on July 5th, 2024 at 12:06 a.m. And that's when the distance from the Earth to the sun will be at 94,510,539 miles. And thus, Earth is farthest from the sun when it's located right here. At this point, the distance from the Earth to the sun will be C plus A, or A plus C. And so at this point, Earth R is 94,510,539 miles. So let's find A and C. So we have A minus C is equal to 91,404,095. And then we have A plus C is 94,510,539. So here are the two equations. Add these two equations together. A plus 8 is 2A. Negative C plus C is 0. And so we get 2A is equal to 185,914,634. Dividing by 2, then we get A is 92,957,317. It is known that the Earth's eccentricity is 0.0167. And so the polar equation for the Earth's orbit around the sun will be R equal to A, which is this number, 92,957,317, times 1 minus E eccentricity squared, dividing by 1 minus 0.0167 times cosine of theta. So this is the equation representing the Earth's orbit around the sun.